In this video, we're going to talk about what a sampling distribution is. Before we get started, I want you to bring your attention to this graphic over here. A sampling distribution always starts with a variable of interest and a measure of that variable of interest. It needs those two things. So, given the times, and this is data that's pulled from 538.com, we want to answer the question, how many Americans are quote unquote very worried about COVID-19's effect on the economy? We get this percentage at 57.2%. Okay, and now I can take that percentage and use it in conversation. I can share it with a colleague, but I also have to be hesitant of that statistic and that number, and I want to think about where it came from. And it goes back to the questions we're taught in elementary school when we read any passage, the five questions here: the where, when, who, what, and how. We have to analyze it and be critical as to where this 57% come from. So let's answer these questions first, and then I'll get into what a sampling distribution is, and we'll look at how to calculate likelihoods and probabilities from such a distribution. So where did it come from? Okay, and now I am speaking on behalf of 538.com. I'm not sure if this is how they used or this is what they did to obtain this value of 57%, but we're going to say in this case that this is what they did. Okay, so let's say where they pulled these people, we'll say we're in the U.S., and let me try to make this bigger so we all can see this a little bit better. All right, we'll say in the U.S. when yesterday, April 12th, 2020, who, and we'll say these were adult Americans, and then what, this is pretty much already answered for us. We're trying to measure worried about the economy. How is really the most important thing. Okay, that's how we want to, like, how was this thing administered? Okay, and let's say that to answer this question, we'll say households from the 2010 census were polled. We'll say households were selected randomly. And the last thing we're going to say is sample size N is say 1,000 households. All right. So ipso facto, 1,000 households, 572. And again, I want to try to make this a little bit bigger here. We'll say our results. We're going to add something to this. Let's make this bigger. We'll say 572 out of 1,000 randomly selected households agreed that they are very worried about COVID effect on the economy. Okay, and let's wrap this text so we can see this a little bit better. All right, and again, I'm not sure that this is how they came up with the 57.2%, but let's just say for the sake of this exercise, this helps us kind of see a little bit deeper into where this number came from. All right, so again, just to clarify on this process a little bit, 1,000 randomly selected households. Think of the House of Representatives. All right, if this is truly random, I would expect that out of this 1,000, there's a higher percentage of California households that are chosen, a higher percentage of New York households that are chosen, a lower percentage of households from North Dakota that are chosen, higher percentage of households from Texas. You get the picture. All right, they're just, think of if every household in the entire country were listed in order from 1 to however many, we're selecting 1,000 from that list. Okay, Now, once we have that percentage, we can use that to explain what a sampling distribution actually is. All right, so it really takes on, the way I like to think about it is it takes on three different things. The first thing that it describes is the range of values a sample statistic can take on. Okay, so what do I mean by that? This 57% is based off of just one sample. Okay, if I were to complete this process again, everything stayed the same. All right, I did the same thing yesterday. I pulled adult Americans. I selected at random 1,000 households. The first thing I want to think about is that group of 1,000 is going to be different. Okay, to some variation, to some degree, it's going to be different than the sample where I got the 57% from. I have to be cognizant of that. Once now I have that new sample, okay, and I pull that sample, all right, I have to believe that the percentage is going to be different, okay, to some degree. Again, maybe now with this sample it's 55%, maybe it's 62%, maybe it's 41%, maybe it's 20%, okay, but that variation can be explained in a sampling distribution. Okay, so this first part, the range of values a sample statistic can take on, is dependent on that variation as it changes from sample to sample. All right. The second requirement is the frequency of such values. Okay, so if I expect to get out of my samples, for the most part, the average is a 57%, then I'm going to expect that most of my samples are going to be right around 57%, whereas samples that are as low as maybe 5% or as high as 82%, the frequency might be a little bit smaller there. Okay, so now think of this visual that I'm depicting here. Okay, and it kind of leads us into our last example, right? And when I say the visual, the ones towards the ends, right, the 5% and the 82%, the frequency is going to be a little bit lower. But as we get to the middle, as we get to the average, the frequency is going to be higher. Okay, what I'm doing is I'm actually naturally building a normal curve. So a sampling distribution, especially for this example, we're going to say is modeled by a normal density curve. Okay, those are the three things I like to think about when we discuss a sampling distribution. It's the range, the frequency, and then go to the normal density curve to make sense of it. And that's what we're going to do next. So remember this 57.2%. Okay, we're going to use it in just a second. And we're going to go over to this website, the Rossmann-Chance applet, just to show you how we get to this. If you go to rossmannchance.com/applets, I'll use this website pretty frequently to explain different things in statistics. And the one we're going to use today is right underneath the tab for statistical inference, and it's the one proportion inference. And if we click on that, it's going to bring us to this page, and you'll notice that it always describes the probability in terms of getting heads or tails. All right. And obviously, our example is different, but it's similar in the sense of it's a binary event. Okay. So when we think about flipping a coin and getting heads or tails, it's binary, meaning there's two options, and that's it. Okay. You get heads or tails. Now, our discussion on what the economy is going to look like and our feelings on that, I'd be naive to think that it's binary. But in the way that we're measuring it here, it's a yes or no question, right? Either you feel very worried about it or you don't. Yes or no. Heads or tails. Binary conversation. So let's say for the sake of this, I'm going to substitute the probability of heads. I want us to think about the probability of being very worried about the economy. So all I'm going to do is I'm going to change this probability to 0.572. Okay, and again, that percentage is coming directly off of this statistic here. All right, so we're going to say that's our probability of success. It was based off sample sizes of 1,000. Okay, and we're going to spare the animation of flipping a coin heads or tails because we're not talking about heads or tails right now. Let's keep going down here. Now, I'm interested in the proportion, not the raw count. So we're going to click on this option for proportion of successes. Skip this for now as extreme. And then you have a couple options here. You have two-sided, exact binomial, and normal approximation. I want you to click on normal approximation, okay? Because when we talk about a sampling distribution, as I mentioned just a couple minutes ago, we often use the normal density curve to model this relationship, okay? So we're going to click on that for now. And let's draw one sample with these statistics. So we're going to click on draw sample. We have one sample. And you'll notice that this little dot that appears, I like that it's not 57.2%. Okay. We're starting to build a sampling distribution. Okay. It's based off of, again, think of this as like the population. Okay. Or think of it as when I flip heads or tails, when I flip a coin heads or tails, I expect in the long run to get 50% heads, right? Well, based off of this statistic that 538 is giving us, in the long run, I would expect most of the time 57% from my samples. But we see some variability here. In fact, the first sample we get is not 57%, it's 59, okay? Let's do another one and see what we get. Okay, so we're gonna click on draw samples. And one thing I like about this website is it keeps a cumulative total for you. Until you hit reset, it'll continue to keep that cumulative total. All right, so the first one we had was at 59%. The second one's a little bit closer to 57. It looks like it's at 56. All right, let's do another one. Okay, this one looks to be right about 57. So that's probably the closest approximation I've gotten so far. Okay, let's do another one. Now we're at 4. Here we start to see some variation. Okay, again, it's further away from that 57%. But up to this point, out of these 4 observations, do you see a normal curve? Okay, I don't see a normal curve. But in theory, what's going to happen is if I do this over and over again, eventually it's going to look like a normal curve. All right, let's keep going without the normal approximation up there. Okay, and then we'll see how close we can get to building a normal curve. Okay, so let's do one more. All right, another one that's a little bit of an outlier. I'm going to rattle off 5 or 6 here. Okay, now we're up to 11. Let's see if we see a normal curve. I still don't see a normal curve. All right, your time is valuable. My time is kind of valuable. Let's speed this thing up a little bit. So instead of drawing one sample here, I want you to change that number to 40. Okay, in the click of a mouse, we can draw 40 samples. Let's click on draw samples and see what we get. Do you see a normal distribution? I still don't. I really don't. Let's keep going. All right, let's change this from 40 to 400. Okay, let's do 400, draw samples. Now do you see a normal distribution? Kinda, right? I'm thinking of like the castle at Disney World, right? This kind of looks like that logo a little bit. Maybe. Let's change it to 4,000. All right, we've had 451 samples. If I change this to 4,000, we're going to be close to 5,000 different samples. And let's see what we get. This might take us a little bit of time. The computer's spinning this one out. So 4,400 samples. Now do we see a normal distribution? Not too bad, right? Let's click on this normal approximation. Let's bring that silhouette back up to compare it. And look at that. It's pretty spot on. There's a little bit of overlap here, but you can see what we experimented with is very, very darn close to that normal approximation, okay? So instead of, again, let's kind of do a full circle here. Let's go back to the definition of a sampling distribution. If we were to do this by hand, draw all of those samples, again, answer the question of that 538 posed about, do you agree that you're very worried about the effect of COVID-19 on the economy? If we were to do that, sample 1,000 people randomly, and then come up with this percentage, and then do that, if we were to do that again for 4,500 more times, it would take you forever. So what sampling distribution tells us is, instead of having to do all of those samples, just jump right to it, where you have this normal approximation. All right, let's hit reset for now. Okay, given just one sample, I'm going to say that I have a normal distribution centered at 57%. Okay, and then I can use all of those rules like 68, 95, 99.7. I can use z-scores. I can use any of those websites that help me with the z-scores. All that applies now to this situation. Okay, so if I have that percentage, I can say that percentage is the average, okay, of my normal curve. Now, if you're being truly critical, and the statistician mind that I want you thinking in is now, well, okay, it's great that this is the middle, but what is the standard deviation? And it's a great question. And we're going to come up with that in the next video.